Okay, let's go over the next example here. And then I'll just add an extra example because I didn't record that first part. Okay, so let's call this number 1. Okay, so we have the following 3 curves. We have y is equal to x cubed, y is equal to 8, and x is equal to 0. Okay, so these 3 curves are going to give us some enclosed region, and we want to rotate the region around the x-axis. Okay, so let's just do a little sketch of this, and then we can use the shell method. Okay, so we've got x and y equals x cubed, that's going to look something like that. Y equals 8, that's somewhere here. Y equals x cubed. X equals 0, that's going to be the y-axis. We already drew that in. So that means this is our region. Okay, so let's color that in. That's our enclosed region. And we want to rotate this around the x-axis. So rotating around the x-axis. Okay, so now we need to find the radius and the height. So let's just draw our vertical rectangle just to get orientated here. So if that's our wall of the shell that's being rotated around, then this distance here is going to be the radius. So that's the radius there. Because remember, the radius is always the distance from the axis of rotation to the point that we're interested in. So we're interested in this rectangle here. So that means the distance, the vertical distance from the rotation axis to the rectangle, that's the radius. Okay, so in this case, the radius is just the y value or the y height. Okay, that's going to be the radius there. Okay, what about the height? The height is going to be this horizontal distance. That's the height there. So in this case, the height is going to be equal to x. Okay, but we don't want to be working with x's and y's. We need to convert everything to y because we're working along this direction. Okay, so that's the direction of integration. So we want everything in terms of y. So if y is equal to x cubed, then x is equal to y to the 1/3. Okay, that gives us the height there. Okay, so I'm just inverting this equation here to get the horizontal distance. Okay, are there any questions about that? Okay, so it's just inverting that to get the horizontal distance x. Okay, and then as for the height, sorry, not the height, the bounds, we're going from 0 to 8. Okay, because that's our y values there. Okay, so we've got the radius, we've got the height, and we've got the bounds. So now we can just substitute everything into the shell method formula. So the volume is going to be the integral from 0 to 8, because those are our bounds. Okay, now we need 2 pi r times the height dy. Okay, because we're integrating along y. So this is going to be 2 pi integral from 0 to 8. The radius is just y, and the height is y to the 1/3 dy. Okay, so that's going to be 2 pi integral from 0 to 8. Y times y to the 3rd, we add the exponents, so we get y to the 4/3. Okay, so simple power rule now. So that's 2 pi. We add 1 to the exponent to make it 7/3. divide by 7 over 3 is the same thing as multiplying by 3 over 7. And then we have y to the 7 over 3. Okay. And then this is going between 0 and 8. Okay, so we're going to end up with 6 pi over 7 times 8 to the 7 over 3. Okay, but just on the side here, 8 to the 7 over 3 is the same thing as 2 cubed to the 7 over 3, which is just 2 to the 7. Okay, because the 3 and the 1/3 cancel there. Okay, so that's going to give us 128. Okay, that's just our powers of 2. Okay, so 128 times 6, that's going to be 768. So we end up with 768 over 7 pi units cubed. Okay, so let's just look at that again. So we've got this region. We are rotating around the x-axis. So with the shell method, if you're rotating around the x-axis, you integrate along y. Okay, so with the shell method, if we rotate around x, okay, or some horizontal axis, we integrate along y. Okay, and then we flip it if we integrate or if we rotate around the other axis. So if we rotate around y, we integrate along x. Okay, and that's if we're using the shell method. Okay, so remember back to the first lecture on the shell method, where I showed you how we cut it up into shells. So if we're rotating around the y-axis, the shells go out horizontally. So we integrate along x. And if we rotate around the x-axis, we see that the shells are going up vertically, so we have to integrate along y. Okay. Are there any questions about that? Okay, so just remember your integration depending on how this thing is being rotated. Okay, let's take a look at another example. Example 2. Okay, so we have y is equal to the square root of 1 minus x squared, rotated around the y-axis. Okay. Now you might be worried, how do you sketch something like this? So just on the side, let me write this down. If y is equal to the square root of 1 minus x squared, then y squared is equal to 1 minus x squared. So y squared plus x squared is equal to 1. So that means this is actually a part of a circle. Okay, so I'm not sure if you saw that last year, but this function here is going to be the first quadrant of a circle. Okay, so this is just a little side note in case you didn't see that. Okay, so how's this going to look? Okay, well, it's the first quadrant of a circle with radius 1. So it's going to look something like that. So this point here is 1, 0. This point here is 0, 1. Okay, so it's just part of a circle in the first quadrant there. So all of this here is going to be our region that we're going to do the rotating with. Okay, so let's color that in. Okay, so we've got that. and we're rotating around the y-axis. Okay, so that means if we're rotating around the y-axis, we're going to have a vertical rectangle here. And this vertical rectangle is going to be rotated around. Okay, so now we need to know the radius, we need to know the height, and then we're good to go. So the y-axis is our rotation axis. So that means this distance over here, is going to be our radius. But that distance is also just x. Okay, so the radius is x. What about the height? The height is just going to be the y value. Okay, that's the height of the rectangle. But the height of the rectangle is also 1 minus x squared. Okay, because it's going to the top of the function. So that's our height. Okay, so we've got the radius, we've got the height. That's everything we need to do the shell method. Okay, because we've already found the bounds. Remember, it goes from 0 to 1. Okay, so the volume is equal to the integral from 0 to 1, 2 pi r. Okay, remember the formula, 2 pi r times h dx. That's our thickness. So this is going to be the integral from 0 to 1, 2 pi x, because that's the radius. And then the height is the square root of 1 minus x squared. dx. Okay, so we see we've got some function x times the square root of 1 minus x squared. You should be thinking this looks like a u substitution, right? Because we've got this outer function being square root, and we've got this inner function being 1 minus x squared. Okay, I hope you haven't forgotten that from all of this volume work that we've been doing. So u is equal to 1 minus x squared. So du is going to be minus 2x dx. Okay, that's almost what we have. We've got 2x dx, but we don't have that minus there. So we take the minus over. So minus du is equal to 2x dx. And that's what we've got here. Okay, so we've done the u substitution part. We found the differential. But remember, if we have a definite integral, okay, so an integral with bounds, that's a definite integral, we also need to change the bounds. So the lower bound was x equals 0. So if we substitute x equals 0, we get 1 minus 0 squared. Okay, so u is going to be 1. If x equals 1, we're going to have 1 minus 1 squared. So that gives us u is equal to 0. So this gives us our new lower bound and our new upper bound. Okay, so that's everything we need for the u substitution. So we're going to have the integral. The new lower bound is 1. The new upper bound is 0. Okay, we still have the pi. And then the square root of 1 minus x squared becomes the square root of u. And 2x dx, that becomes minus du. Okay, so that's everything substituted now. So we can take the constants out. So we have minus pi, integral from 1 to 0, u to the 1/2 du. Okay, now the bounds are swapped. Okay, so we should have the lower bound being smaller than the upper bound, but that's fine because if we have a minus in front of a definite integral, we can swap the bounds. So this now becomes pi integral from 0 to 1. Okay, we can swap them if we got the minus sign in front. U to the 1/2 du. Okay, so now we don't have to worry about that minus sign getting in the way. So let's do the integral. So we have pi We add 1 to the exponent to make it 3 over 2. Divide by 3 over 2 is the same thing as multiplying by 2 over 3. U to the 3 over 2 from 0 to 1. So we get 2 pi over 3 units cubed. Okay. So this question had a little bit extra step with the U substitution. So something like this in the test will be worth a few more marks than usual. Okay, because you've got all of this stuff to do as well. Okay, so this will count a bit more. Yeah, but it's exactly the same procedure. So once you found your radius and your height, then it just becomes a normal integral. Okay, so you forget about the volume stuff. It's just a normal integral that you then need to solve. So if it becomes something with sine and cosine, you should be able to integrate that. If you have to do a U substitution, then you can do that, and so on. Okay, so it's just a normal integral that you have to solve. Okay, so sometimes you will need to do a U substitution. Okay, just like in that homework problem that I set some time ago. Okay. Are there any questions on this one? Okay, got a question here. Do we have to substitute U at the end? No, there's no substituting U at the end because this is a definite integral. Okay, so this is a definite integral. Okay, so we change the bounds instead of substituting back U. Okay, so we see here, once we've converted everything to U, then we just get a number at the end. So there's no reason to substitute U back. Okay, so at this step here, okay, we just substitute the bounds and we get a number in the end. So it's not like indefinite integrals where you have to put the function back to get a function of x. In this case, we get our number in the end, so there's no reason to do the substitution again. So we get the number, or we get a number in the end. Okay, so you don't have to substitute back. Okay, cool. Got another question here. Please go over it from the U substitution part. Okay, so let's just go to the U substitution part. So here at the U substitution, we see that we've got a square root of 1 minus x squared. Okay, so we've done these types of things a lot with U substitution, square roots of something. So you should always keep in mind, if you have the square roots of something, like here, then you should be using U substitution. Okay, that's the first thing that should come to your mind. So that's what we do. So we look inside the square root, we get 1 minus x squared. That's the inside part. So this inside part becomes U. Okay, so U equals 1 minus x squared. We take the derivative to find du. So du will be minus 2x dx. Okay, so we just used the derivative, du by dx dx. Okay, we've done a lot of that. Okay, so we get minus 2x dx. We see that in the integral, we actually have 2x dx. I've underlined that in blue. So we take the minus 1 to the other side. So we get minus du is equal to 2x dx. Okay, so that gives us this part here, which is this part here. Okay, so that's the first 2 steps of U substitution. Doing the U substitution there, finding the differential. But remember, there's an extra 3rd step if it's a definite integral. So we need to change the bounds. So the lower bound was x equals 0, and the new lower bound will be 1, because we have 1 minus 0 squared. 1 minus 0 squared, and the other one is 1 minus 1 squared. Okay, so 1 minus 0 squared, the new lower bound is 1. So we got that there. Okay, 1 minus 1 squared gives us 0, so that is the new upper bound. Okay, so we've substituted in u into our square roots, and we've substituted 2x dx, which is minus du. We take the minus pi outside, but we notice that the integral has swapped bounds because 1 is at the bottom and 0 is at the top. Okay, that's a problem, but we can fix that because we've got the minus in front. So if you have a minus in front, you can swap the bounds of integration. So remember, minus the integral from a to b, f of x dx, is equal to the integral from b to a, f of x dx. Okay, so these swap if you got the minus sign. Yeah, so they swap if you got the minus sign there. So we swap that and then just do the integral. So u to the 1/2, we add 1 to make it 3 over 2, divide by that, substitute the upper and lower bounds, and we get our final answer. Another question here, do we always change the bounds? Yes, of course. So if you have a definite integral and you're using u substitution, you always change the bounds. Okay, you always change it with a u substitution. Okay, remember back when we did u substitution? Where's this? There we go. U substitution with definite integrals. Back at lecture 13, if you want to rewatch that, you always have to change the bounds. So here I'll put big. This is the extra step that we need to do, is changing the bounds. So here we can see with this example here, the old bounds were 0 to 1. Those were the x bounds. Now the u bounds go from 0 to pi over 2. Okay, so please go back to lecture 13 if you want to go over that again. Okay. Okay, cool. No more questions there. Okay. Let's have a look at one more example. Okay, so I just want to go over that homework problem that we had. Sorry. Okay, so this was the homework problem from yesterday. We had x is equal to 2y squared and x is equal to y squared plus 1. Okay, so we see we have x and y, they have swapped their roles. Okay, so if we were to sketch this, we just need to shift our thinking. So instead of having y as a function of x, we now have x as a function of y. So x equals 2y squared. We just have to draw it like this. Okay, because x and y flip around. So just think about flipping x and y around. That we just sketch it as normal. It's just the variables have swapped around. Okay, and x equals y squared plus 1. That's going to look something like this. Sorry, let's just draw that a bit better. Something like that. So if you just turn the screen, it looks exactly the same as if y was a function of x. Okay, but now x is a function of y. So we have x is equal to y squared plus 1. So that point there is 1. And then the other one is x equals 2y squared. Okay, again, it's exactly the same as sketching y as a function of x, but you just need to turn your head to the side because x is now a function of y. Okay, so the enclosed region is going to be this part over here. Okay, that's the part enclosed by these two curves. Okay, and we are rotating around y equals -2. So that's going to be somewhere here. Okay, rotating around. So we need to find the radius and the height. So let's do the radius first. So if this is our rectangle, okay, remember the rectangle is always parallel to your rotation axis. So if your rotation axis is horizontal, then your rectangle is also horizontal. So this distance here is the radius, and this distance over there is the height. Okay, so what's the radius going to be? The radius is going to be y minus -2, because we're shifting by -2 there. So the radius is going to be y plus 2. Okay, and what about the height? Okay, so that's the radius. The height is going to be the upper function minus the lower function. So this is the upper function. Okay, that's the upper function there because it has the greater x value. So it's going to be y squared plus 1 minus 2y squared. Okay, because x equals 2y squared, that is below the other one in terms of x. So h is equal to 1 minus y squared. Okay, so we've got the radius, we've got the height, we can then substitute in. So the volume is going to be equal to the integral from -1 to 1. Okay, because we're going from y equals -1 to y equals 1. Okay, I'll let you check that these are the intercepts here and here. Okay, at -1 and 1. Okay, it's going to be 2 pi times the radius, but the radius is y plus 2. And the height is 1 minus y squared, dy. Okay, so we can take the 2 pi out. And we can expand the brackets. So we're going to get y minus y cubed plus 2 minus 2y squared. Okay, dy. That's going to be 2 pi. We integrate this. So we're going to get 2y minus 1/4 y to the 4. Sorry, that's 1/2 y squared plus 2y minus 2 over 3y cubed from -1 to 1. Okay, then you substitute 1, you substitute -1. You can check that for yourself there. We end up with 16 pi over 3 units cubed. Okay. So besides the integration, that's pretty easy to do. The only thing different here is that this axis of rotation has been shifted. Okay, so it's been shifted here to y equals -2. But we do exactly the same thing as if we were doing the disk method or the washer method. Okay, so we want to find this distance r. We know the top part here is y. So that's at point y. So if we want to know the distance, it's going to be y minus -2. Okay, and then the minus and the minus make a plus. So we end up with y plus 2. Okay, and then the height, exactly the same as we had before. It's the upper function, which is y squared plus 1, minus the lower function, which is 2y squared. That gives us the height. And then the rest is exactly the same. So volume is the integral, -1 to 1, 2 pi r, that's the circumference, times h dy. Okay, exactly the same as what we've had before. Okay. Any questions on this one? Okay, so it's not too bad. so you have the tutorial questions to do over the weekend. Okay, there's quite a few examples there to go through. And then I will also post a homework question on the WhatsApp group. And like last time, it will be worth 1 or 2 extra marks for your next tutorial quiz. Okay, coming up on Wednesday. Okay, so I'll do that after this. Okay, if you do have any questions later on, please just post them on the WhatsApp group, or you can send me an email if you want, and then I can help you out with that. Okay, we also have the tutors on the WhatsApp group, so you can ask them as well. Okay, they should be available to help you out. Okay, and then next week, Monday, we will start on the new section on integration by parts. Okay, so we're going to go back to integration techniques. Okay, we're going to leave this volume stuff alone. Okay, so that's the plan for next week. And remember, we've got the test coming up on the 6th of April. Okay, so I hope everyone is preparing for that. Okay, bye everyone, and enjoy your weekend. I'll see you Monday.